Okay, in this lecture we're going to look at a system of linear differential equations and how those are solved. The system can be written quite simply as y dot equals ay plus b, where a is an n by m matrix of constant coefficients, y is a vector of n variables, and b is a vector of n constant terms. We can rewrite that in the case of two equations as y1 dot is equal to a1 y1 plus a1 y2 plus b1. It's the b1 part that makes it non-homogeneous. We do the same thing for equation 2, and we can simplify this as a system written in matrix notation as, or y dot is equal to ay plus b. Now there's two ways to solve this particular problem. One is the direct method, and in that case, to solve such a system, we again add the homogeneous solutions and the particular solutions, but we begin with the homogeneous solutions, so we can write y dot equals a times y, where a is that matrix, y is a vector, and y dot is a vector. We can guess that the solution has to take the following form. Y is equal to k, where k is a vector of n constants, times e to the power lambda t, where lambda is a scalar and k a vector of these n constants. Take the derivative of 2 and we get y dot is equal to lambda times k e to the lambda t. We substitute 3, this equation, into 2, and we get this result here that lambda k e to the lambda t is equal to a k e to the lambda t, which can then be rewritten as, by canceling these terms here, as a minus lambda I times k is equal to 0. In other words, either k is 0 or this expression a minus lambda I, where I is an identity matrix and 0 is a vector of zeros. Recall that 4 has a non-trivial solution only if, that means it's non-trivial, only if the determinant of a minus lambda I is equal to 0. If it was trivial, we'd have simply that k was equal to 0, which doesn't help us at all. So now, using the general form, we find the determinant of this expression, which is the characteristic equation of a, that is this equation here. And what we want to do is find the eigenvalues and the eigenvectors of a. So let's look at that two-dimensional case. We can write that as a11 minus lambda, a21, a12, and a22 minus lambda, set it equal to 0. We get this equation here. And you'll notice that this equation has lambda squared minus a11 plus a22. That's simply the trace of the original A matrix multiplied by this lambda. And this is the determinant of that original A matrix. And you can see that in this expression here. Then using the quadratic formula, we find that lambda 1 and lambda 2 are given by the trace of A over 2 plus or minus 1/2 times the square root of the trace of A all squared minus 4 times the determinant of A. So let's consider the example from Hoy et al., where we have y dot equals A matrix times y, where the A matrix is given by 4, minus 1, minus 4, and 4. We can write that in this form here, if we write the two equations separately. And then we can find the determinant of A minus lambda times the identity matrix. And solving that, we get the solution that lambda 1 is 2 and lambda 2 is 6. Now we want to find the eigenvectors, and we do that in the standard way by looking at first the eigenvector for lambda 1, where we subtract 2 from the original up here. So 4 minus 2 is 2 minus 4 minus 1, and again 2 here. So we get one equation, since both of these end up with the same result, that 2k1 minus k2 equals 0. We just choose k1 to be 1, so that k2 is 2, and we get this eigenvector here. So the first set of solutions, which we denote with this superscript 1, is equal to this eigenvector 1, 2 multiplied by e to the power 2 times t, where that 2 comes from the solution of the eigenvalue for 1. Now, if we take the second eigenvalue, where we have a 6, then we can do exactly the same thing, but notice that the k1 and k2 here are different from the ones we considered up above. In this case, again, we get one equation, minus 2k1 minus k2 is 0. We can set k1 equal to 1, and now we get k2 being minus 2, so we get this second set of solutions where y superscript 2, denoting the second set, is y is equal to 1, the vector 1 minus 2 times e to the 6t. Since the solutions are linearly independent, the general solution is given by yt times c1 times this vector e to the power 2t plus c2, this vector 1 minus 2 e to the power 6t. And we can write that out in this form here, these two equations. What about a particular solution? Well, consider again y dot equals ay plus b. A particular solution is found by setting y dot equal to 0. We get this equation here in that case, and the solution is then given by minus the matrix A inverse times b, and we note that the determinant of A cannot equal to 0. Now this is quite easy, because what you can do in R, it's very easy in R to find the eigenvalues, the eigenvectors, and A minus 1. A minus 1 can be found simply using this expression here, solve. All right, then we have to create the matrix C, and then A1, 1, A1, 2, A2, 1, A2, 2, and we're going to make that a 2 by 2 matrix, 2 by 2, by row equals true. Let me just, by row is true, and we need to make sure we got these matching brackets. So that's how you get A minus 1. One can transform a second-order linear differential equation into a system of first-order linear differential equations. Suppose you have this expression here, this second-order linear differential equation, y double dot minus a1 y dot minus a2 y equals b. We define x to be y dot, so then we take the derivative of x, which is x dot equals to y double dot. Substituting that into this expression here, we get x dot equals, and we're moving this onto the other side, a1x plus a2y plus b, and y dot is equal to x. So we can rewrite that in this form here, where this big Y dot is equal to a vector x dot y dot, and we get this expression here, where A is given by that matrix. All right, so we had the direct method, and now we're looking at the substitution method. Consider again a linear system of two autonomous differential equations. We've seen this one before. That's the one we solved above. The solutions are y1, that y1 to the h, y1 to the p, where h refers to the homogeneous solution, p to the particular solution. In the past, I've used an n to denote non-homogeneous. Here I've used a p to denote particular solution. We do the same thing with y2, and the idea is to convert the system of two first-order differential equations into a single second-order differential equation. That's the idea behind the substitution method. So consider the homogeneous form of those equations, which is given by this here, and we want to differentiate the first equation, this one here, with respect to time, and we get y double dot y1, a11 y1 dot plus a12 y2 dot. All right. Now substitute the second equation into the above, and we get y1 double dot equals a1 y1 dot plus a12 a21 y1 plus a12 a22 y2. We solve the first equation for y2, so we solve this equation here, for y2, and we get the following, and we substitute that in for this y2 here. Notice that that a12 cancels, or will cancel that a12 there. So when we substitute in, we get this expression, and notice that we've canceled out that one there, and we get that y1 double dot is given by, we have a y1 dot here and a y1, and we rearrange it like this so that it looks in like our traditional second order differential equation, which we then solve in the normal way. For the substitution method, we also have to consider the particular solution. So we set y1 dot and y2 dot equal to 0, and we substitute in for the y1 and the y2, a y1 bar and a y2 bar respectively, and solve the resulting two equations, these two here. We solve those for y1 bar and y2 bar, where y1 bar and y2 bar are the particular solutions. And that gives us these two results when you do that. And solutions exist only if, that's if and only if, this expression underneath here, which is the same under both of them, is not equal to 0. These particular solutions are then added to the homogeneous. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.